Hello, for today's video lecture we're going to be talking about the one-dimensional equations of motion. So getting into this chapter, we're going to be using Newton's second law and particularly the force acceleration method for kinetics. So the force, mass, and acceleration method in kinetics is going to build directly on Newton's second law, which states that the sum of the forces is equal to the mass times the acceleration. So if we add the known and unknown values into this equation, so known forces or known accelerations, it becomes known as the equation of motion. And we're going to be solving the equation of motion as part of this whole process. So it's important to remember that the F forces and accelerations are vectors. So in many cases we're going to be breaking these down into components in either x and y direction, normal and tangential direction, r and theta direction. And we'd have an equation of motion for each component direction. So by solving this equation or equations later on, we can find either the forces given something we know something about the accelerations, or the accelerations given that we know something about the forces. All right, so in one dimension, we're going to start by analyzing motion here. So when we have only one direction of motion possible or likely, we can use a single equation of motion. Kind of our vector equation just becomes a regular scalar equation. So in this case, we're going to use the x direction to indicate the single direction that we're using. And the sum of forces in the x direction will be equal to the mass of the object we're looking at times the acceleration of that object in the x direction. Here we're looking at we may have forces in other directions, but we should only pay attention to the forces or force components that are going to be in that direction. So here we've got a block. It's sitting on an icy surface. It's got some mass m, and the force in the x direction would be equal to the mass of the block times ax, which is the acceleration in the x direction. Fg, the gravity force, and the normal force don't get put into this equation because they're not acting in the x direction, they're acting in the y direction. Alright, so Newton's second law over time as well is an option. So in the original equation, we relate force, mass, and acceleration at some given instant in time. So the force at any one point would be equal to the mass times the acceleration at that point in time, that instant in time. But we can also, if we look beyond a given instant, we can still apply this equation to a force function and an acceleration function. So if I've got some force that's changing over time, we can multiply. If we multiply the mass times that acceleration function over time, this would also hold true. This would put an equation for force and an equation for acceleration over time on both sides of this. The mass usually is constant for any given body. There are also some instances where the mass might be changing over time. An example of that would be something like a rocket booster, where a significant amount of the weight is in the fuel, and as the fuel is burned, the mass of that rocket is going to be changing as well. So you'd have an m of t term in there as well. But all in all, this will still hold true no matter how simple, a given force, a given acceleration at a time, or an entire force function, an entire acceleration function over time as well. All right, so with mass, you do want to be careful. So in the metric system, it's pretty easy. The mass of the object is usually given in kilograms, but in the English system, we usually talk about weight. So I might say something weighs 100 pounds. And 100 pounds is not a mass. 100 pounds is a force, or particularly a weight force in this case. So weight is not the same as mass, so we need to talk about the English unit of mass, which is, we would divide that weight by g, similar to how if we take the weight of something in newtons divided by g, it would give us the kilograms, and the equivalent in the English system is slugs. Slugs is not a unit that people see very often, but we need to use slugs in this F equals ma equation. And so a slug is 1 pound second squared per foot is the definition of a slug. And if you think about this, on the surface of the Earth, one slug is going to weigh 32.2 pounds. But the difference is, if you go up into space, your weight would change as the acceleration due to gravity changes, but your mass would still be the same no matter where you go. All right, so going back, solving a kinetics problem, bringing the whole thing together, the process, it's going to be similar to solving a problem in statics and consists of 3 steps. So to start any kinetics problem, we're going to set up a free body diagram, which involves drawing the body separated from its surroundings. Then you want to draw in all known and unknown forces. Personally, I use red for forces in my diagrams. And then we also want to draw in any key dimensions or angles. For now, particularly the angles of those forces are going to be important. And I use blue for dimensions and angles. And I also, in the dynamics problems, I like to draw in my acceleration vector. So I personally will use a blue dashed vector for this acceleration to differentiate it from forces, differentiate it from the dimensions and angles. Next, we're going to use the free body diagram to write out our equation for now, or equations of motion later on. So that's the F equals ma. Put in what you know about the forces, put in what you know about the accelerations. And then step number 3, once you have your equations of motion set up, you use the known values to solve for the unknown values. You might be solving for forces, you might be solving for accelerations, you might be solving for something about velocity, which you're going to have to derive from the accelerations you would find in this equation. So that's all I have for today's video lecture. Thank you for watching, and I hope to see you again.